So last time we've been talking about two particularly important topics in linear algebra. One of them is span. So we started talking about linear combinations of vectors and how the span of a set of vectors is the set of all linear combinations of those vectors. And we saw that in itself, the span of a set of vectors is itself a subspace. So that's we focused a bulk of our time last lecture in understanding span. And we'll come back to span again. And now at the end, we start talking about linear independence. And so linear independence of vectors so if I have vectors v1, v2, all the way to vn, if I have n vectors and I want to demonstrate that these are linearly independent vectors, then when you do the equation C1v1, C2v2, all the way to Cn/Vn, and you set this equal to 0. So just to compare this, normally when we deal with span, we want to figure out whether a vector is in the span of a set of vectors. So we normally set up this equation very similarly, right? We set up our linear combination of vectors, and then we set the vector that we're interested in, whether to figure out whether or not this system here has solutions where the solutions would be the coefficients of our vectors. So, and then normally this kind of equation results in having a system of equations, and then we can create a matrix equation where really it boils down to whether the coefficient matrix that we have, whether that coefficient matrix is an invertible matrix or not, which you can determine by finding the determinant of that matrix. But now we're dealing with the fact, in a sense, we're saying that whether v1, v2, vn, the span of these set of vectors to create the zero vector is only if the coefficients themselves are all zeros. If the only way to write 0 as a linear combination of the vectors v1 through vn, if the only way to write that is if the coefficients are all zeros, then we say that the set of vectors are linearly independent. If and only if C1, C2, all the way to Cn equals 0. So that's what linear independence means. Okay. So let's look at an example. I want to show, or determine, I should say, determine whether these vectors are linearly independent or not. Okay, so then how do we go about doing this? Well, we consider this as our first vector, as our second vector, and as our third vector. And I want to know whether it's linearly independent, and these vectors live in the vector space R3. So normally we do is we set up the same kind of equation here. Right, So we want to see what happens when we set up this linear combinations of V1, V2, V3. So this will look like what? This will look like C1 -304 plus C2 5 -1 2 plus C3, and this should be a little bit more clear. So this is 1 1 3 equals 0 0 0. And then when we distribute the C1, multiply the scalar multiplication, I get -3C1 0 4C1 plus 5C2 -C2 2C2 plus C3 C3 3C3 0 0 0. And then what happens? I add everything component wise, and I get a system of equations, a particularly non-homogeneous system. Pardon me, a homogeneous system of equations. Right? This is a homogeneous system. And then what happens with this? The problem now transformed itself from, hey, what are the C1, C2, C3 in this linear combination of V1, V2, V3 that would give me 0? This transforms itself into saying whether or not this homogeneous system has solutions, or if it has more than one solution, or if it's no solution, or if there's only a unique solution. And so I can create a matrix equation, -3, 5, 1, 0, -1, 1, 4, 2, 3. I got C1, C2, C3. This is 0, 0, 0. So now I transformed this this one single equation, this vector equation, and I transformed it into a matrix equation. And so now the question is, hey, do I have a solution? Is there one solution? Is there many, infinitely many, or is there none? So this is dependent upon whether or not this here, the determinant of this matrix is 0 or not, because that determines whether a matrix is invertible, and it tells us whether there's a unique solution to this or if there isn't. So right now my calculator on my computer is not working. So I will do this by hand. And again, I only care, so I'm going to find a determinant, and I only care about whether or not it's in the determinant is 0 or it's not 0. So then I'm going to include this additional column, both columns, column 1 and 2. And then we can calculate the products of these numbers here. This is 0, this is -6, this is -4. So this is, if you put them all together, if you add them up, you get -10. And then if you go the other way, this is +9, this is +20, and we get 0 again. So when you add these up, you get 29. And the idea is that you subtract these numbers, right? You subtract to get the determinant. To the determinant, it will be 29 minus -10, which is 39, which is non-zero. So what does this mean? This means that since this is non-zero, this means that inverse exists. If the inverse exists, then that means that there's a unique solution to the system. If there's a unique solution to the system, so if this is A, right? I'm gonna call this C, I'm gonna call this B. So that means that A inverse exists. And if A times C equals B, then C is equal to A inverse of B. But B is 0. This is the 0 vector. So let me write this as this. So I'm multiplying the matrix, the inverse of A by 0. But what does that mean? It's 0. So what did I just show? I showed that C1 has to be 0, C2 has to be 0, and C3 has to be 0. And there can't be any other values for C1, C2, or C3 because it's unique. It's unique. It's unique. There's only one. When you multiply 0 by this matrix, inverse matrix, the only thing that would produce would be 0. There's no other alternative. So then what did I just show? So hence what? Hence V1, V2, V3 are indeed linearly independent in R3. Okay, does that make sense, guys? Does this make sense as to why they're linearly independent? Very similar in terms of the approach for spanning, very similar. It has to deal with the matrix equation that eventually is formed and determining whether the solution exists for that system boils down to whether or not the determinant of the coefficient matrix is a non-zero or a zero value. Okay. Okay, so so we know how to deal with matrices, with vectors. So what happens if I have a matrix, a set of matrices? So let's say I want to determine, determine whether this set of matrices are linearly independent. Remember what M22 is? It's the space of all 2 by 2 matrices. Okay, so we have 3 matrices from this world, and I want to know whether these matrices themselves are linearly independent or not, or dependent. So the idea boils down to the same thing we've done. So I'm gonna call this M1. I'm gonna use a lowercase. Okay, so I'm gonna call this M1, M2, and M3. So these are 3 matrices. So then what would I do? I'll write this as C1, M1 plus C2, M2 plus C3, M3. This has to equal the 0 matrix, right? Which is 0, 0, 0, 0. So this is what I have. It's the same idea with vectors. Now I'm just applying that formula or that equation to matrices. So this would be C1. Then I got 1, 1, 0, 1, 2 plus C2, 1, 2, 2, 1 plus C3, 0, 2, 1, 1. And this equals 1, 0, 0, 0, 0. And then when you apply the multiplication of scalar multiplication, what do I get? I get C1, 0, C1, 2C1 plus C2, 2C2, 2C2, C2 plus, and I get 0, I get C3, I get 2C3, and I get C3. And this equals 0, 0, 0, 0. And then when I add everything together, I get a 2 by 2 matrix that says the first component is C1 plus C2. And then the next component here would be 2C2 plus C3. This would be C1 plus 2C2 plus 2C3. And then I get 2C1 plus C2 plus C3. They all equal 0. And now individually, what do I get? I get C1 plus C2 has to equal 0. I get 2C2 plus C3 has to be 0. So let me just rearrange this. So this is written now as a system. This is 2C2 plus 2C3 is 0. And I get 2C1 plus C2 plus C3 equals 0. What kind of system do I have? I have what's called an overdetermined system. It's called overdetermined because I have more equations than variables. It's kind of like saying I have more equations than needed. So I have an overdetermined system. I got 4 equations, and I have 3 unknowns. An underdetermined system is when the opposite happens, when you have more unknowns than equations, then that's called an underdetermined system. And most of the time, those kind of systems have infinitely many solutions. So from here, what can I create? I can create a matrix equation, and I can create, this is 1, 1, a 0. This is 0, 2, 1. This is 1, 2, 2, and this is 2, 1, 1. This is a 4 by 3 matrix, and this is C1, C2, C3. And I get 0, 0, 0, 0. Now, this is a scenario where you cannot determine whether or not C1, C2, C3 are only the 0 values just by applying the determinant, because the determinant of a non-square matrix is not possible. This is a non-square matrix because the number of rows do not equal the number of columns. So we can't apply the determinant here. But what we could do is to try to figure out row reduced echelon form. So that should be a way to help determining whether a linear system like this has a solution and what that solution might be. So let's try to quickly row reduce this. We can eliminate the 1 and the 2 here. If we do negative R1 plus R3 into R3, and negative 2R1 plus R3 into R3 for R4, plus R4 into R4. So I'm just looking at the matrix here. So this would be 1, 1, 0. This is already 0, 2, 1. This will be 0, and this will be 0. I'm subtracting, so this will be 1. This will be 2. And this will be 0, and I'm subtracting. So I get negative 1, 1. And what I'm going to do is I'm going to swap row 2 with row 3. And I get 1, 1, 0. I get 0, 1, 2. And I get 0, 2, 1. And I get 0, negative 1, 1. So then from here, I can eliminate the negative. So I do negative 2R2 and add it to R3 into R3. So this is 1, 1, 0, 0, 1, 2. So when you multiply by negative 2, you get 0. And then when you multiply negative 2, you get negative 4 plus 1 is negative 3. And then here, you get negative R2 plus R4 into R4. So when you add that, you get 0 here. And then you get 1. Sorry, you get -1. And so what happens when you continue with this, what happens? I can negate, yeah, the fourth row is a multiple of the third. That's right. So I can do various things. I can just uh, divide this by a third if I want, right? Into R3. And then, so this is the first step. And then the second step is take R3 and add it to R4 into R4. So then what's the result of these two steps here? I get 1, 1, 0, 0, 1, 2, 0, 0, 1, and I get 0, 0, 0. And then without having to fill in all the rest of the details, I realize I can get rid of the 2 and the 1. And so what do I have? I get 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. Now, this is my row reduced echelon form of my original coefficient matrix. But what does this information tell me? Well, given the fact that this is a homogeneous system, what I just showed you was that C1 equals 0, C2 equals 0, and that C3 equals 0. That's what this information here in the row reduced echelon form of this matrix tells me. So this tells me that C1, C2, C3 must be 0. If it must be 0, and that's the only values that C1, C2, C3 are, then the result is what? Then we say, hence, the matrices that we originally started with, 1, 0, 1, 2, 1, 2, 2, 1, and 0, 2, 1, 1 are linearly independent. In M22. So we have a linearly independent set of matrices. Yes, that's right, Sam and Satar. So the reason why we couldn't use matrix determinants the way we normally would for this particular example is because we have what's called an overdetermined system, which would create a coefficient matrix that is a non-square matrix. And if you remember back in the day, when we first talked about determinants, we say that the determinants are only applied for square matrices. So the whole idea of cofactor expansion, that whole idea only is applied to square matrices, not non-square. So we can't apply the determinant because there's no way to do so if you have a matrix that is a non-square. So then the only thing that would work for any matrix, no matter if it's square or non-square, is the idea of row reduced echelon form. So we go back to the beginning, going back to the basics. So don't ever forget the basics. You need to understand the basics really, really well, so that when things such as the determinant breaks down, we can go back to something that will never break down. The row reduced echelon form, that Gaussian Jordan elimination process, is always good, always is applicable when you want to solve systems of equations. It's just that now we're more sophisticated because with determinants. But again, determinants fail in the realm that when we deal with matrices that are non-square, such as this one. So then to determine what the solution of the system is, we have to perform Gauss-Jordan elimination. And we found that the solutions are only zeros for the coefficients of our original matrix here. I guess you can say the matrix equation. So we just showed that the only way that these matrices, the only linear combination of these matrices to give me the zero matrix is if all the coefficients themselves are zeros. And because they're the only ones that are zeros, then they form a linearly independent set of matrices in the space of 2 by 2 matrices. So that's how we deal with these kind of linear independence questions. So if you start to notice, it's kind of, we're applying the same kind of approach to determine whether vectors are linearly independent, whether matrices are linearly independent. And so the other vector space that we like to figure out are polynomials. So if we're in the set of P2, so determine whether, we'll call it P1, 2 minus x plus 4x squared, P2, 3 plus 6x plus 2x squared, and then P3. We did something similar to this when we were talking about spanning. So determine whether these polynomials are linearly independent. In the space P2. So again, P2 is the space of polynomials that have a degree less than or equal to 2. So all of these are polynomials in this space. I want to know whether they're independent or not. So I do C1 P1 plus C2 P2 times P2 plus C3 P3. Is this the polynomial 0? Again, the polynomial 0 would be what? It would be 0 plus 0x plus 0x squared. Okay, so always try to understand the underlying vector space that you're in. So we're in the vector space P2. So our 0 vector, quote unquote, in P2 is this similar to what? The 0 vector in R3. So start to see, wait a minute, there's like a connection between P2 and R3. Why? Because in P2, in the world of P2, our objects, in this case, polynomials in P2, have 3 terms. The 2 is not for the number of terms, but the 2 deals with degree. If you have a polynomial degree 2, you have 3 terms. You have a constant term, a linear term, and an x squared term. And each of these terms have certain coefficients to them. So this here can be treated as a vector 0, 0, 0 in R3. So I think I mentioned this before. There's a connection between different vector spaces. Despite the fact that we're dealing with polynomials here and we're dealing with vectors over here, there's something that's similar in the structure behind these two apparently distinct vector spaces that make them quite the same. So then what does this become? C1, this is what? 2 minus x plus 4x squared plus C2 is 3 plus 6x plus 2x squared plus C3. C3 is 2 plus 10x minus 4x squared. And all of this is being equal to 0 plus 0x plus 0x squared. When you distribute the C1s, you get 2C1 minus C1 plus 4C1x squared. This is 3C2 plus 6C2x plus 2C2x squared plus 2C3 plus 10C3x minus 4C3x squared equals 0 plus 0x plus 0x squared. And then what can I combine? I combine all of the 2C1, the constant terms, 3C2 and the plus 2C3. This here is the constant term. Then I'm going to add all of the linear terms. Forgot the x here, so I have the linear term here. So here this here and this here. When I put them together, I get minus C1 plus 6C2 plus 10C3, and this is times x. And then finally, I'm going to put all of the x squared terms and associate them together, and I get 4C1 plus 2C2 minus 4C3 x squared. This equals 0. 0. Just move this a bit to the left. This is 0 plus 0x plus 0x squared. So I'm saying this polynomial on the left, the way this looks here, has to equal the polynomial on the right. The only way that's possible is if this equals 0, and these coefficients together equal 0. So this has to equal 0, this has to equal 0, and this has to equal 0. So look what I get. I get a system of equations again. I get 2C1 plus 3C2 plus 2C3. This equals 0. I get negative C1 plus 6C2 plus 10C3. This equals 0. And I get 4C1 plus 2C2 minus 4C3. This equals 0. And then when I create the so Tasa, can you use other variables? The simple answer is of course. Of course you can. It's just a convention. It's conventionally C1, C2, C3 are conventionally used, but inherently there's no difference, right? You can use A, B, C. You can do another letter that you would prefer. But it's just, you have to, like, for example, it wouldn't make sense to use x1, x2, x3. Why not? Because the variable for polynomials that we usually utilize are x's. So it would be a little bit more clunky, right? If I were to say this is x1, if I were to say this is x1, x2, x3, which I can, but then I have to, don't get confused with the x's that I have here and make sure that they understand that they're different. So that's why normally they use C1, C2, C3, because we start from the beginning, we're dealing with the coefficients we're dealing with the coefficients of vectors. In this case, they're polynomials. And so if you prefer another set of letters, great. Just make sure you know what you're doing when you do that. But like I said, it's convention to utilize C1, C2, C3, because then from here I can write a matrix equation. So this is my matrix equation. 2, 3, 2, negative 1, 6, 10, 4, 2, negative 4. It's my coefficient. And my column vector is C1, C2, C3, which is the coefficients of my polynomials, and I get 0, 0, 0. And so this boils down to knowing whether or not C1, C2, C3 has a unique solution to this homogeneous system boils down to whether or not this square matrix has a determinant of 0 or not. So for here, the reason why we use the determinant for this is because it's just the quickest way to determine whether we have a unique solution to this homogeneous system or not. Again, we've done the longer way, which is the row reduced echelon form. But just to make our lives a bit easier, I'm going to plug this in. So I'm going to do this in my calculator. And I hope you guys are able to do it in yours. And you should know now how to do these things. So I plugged in the entries of this coefficient matrix. And now I'm going to simply compute the determinant of this matrix that I created in my calculator. And I get the determinant is negative 32, but I don't really care about the number. I just care the fact that it's 0, which would indicate that A is what? A is invertible. If A is invertible in this equation, in this matrix equation, then I know that a unique solution exists. if there's a unique solution that exists in a homogeneous system, that means that the only solution that exists would be if C1, C2, C3 all equal 0. If C1, C2, C3 is the only unique solution to this homogeneous system, then what do we say? We conclude that our polynomials then, so we say hence P1, P2, P3 are linearly independent. They're linearly independent polynomials in P2. Any questions about linear independence? Being linearly independent in the space of polynomials, in the space of matrices, or in the space of just standard vectors? Mir. Okay, so the geometric understanding of this would be well, you have to be careful with that they only intersect at the origin, because what are you referring to as they? Are you referring to as the polynomials only intersecting at the origin? That wouldn't make much sense because, well, let me see, polynomials here. If you were to graph these, what would you get? So maybe that's an interesting point. So let's see.
No, but there is a unique solution, so I have to be wrong.
Well, the thing is, no, all I want to ask, all I brought that up, the only thing I brought up was, what are you referring to when you say they? Are you referring to the set of polynomials, or are you referring that they only intersect as the set of vectors? Because the vectors that are linearly independent are the columns. These columns, if you were to graph these in R3, then the only point of intersection would be the origin. That's what it means to be linearly independent in R3. And let me just, hold on, let me. Yeah, so that's the only reason why I brought this up, was because if you graph these three quadratic functions, then you get something like this. I'm gonna try to draw it. So you get something like this. Something like this. You get something of this sort, but as you can tell, they don't intersect at the origin, but they are linearly independent. So just be careful with that. So the polynomials themselves, they're linearly independent. Why? They're linearly independent because when you set up this equation, the only C1, C2, C3 values that are possible to make this equation true is if they're all zeros. That's what makes them linearly independent. But if you're looking at this in the world of R3, then what you're saying is the coefficients of these polynomials. So 2, -1, 4, that's one vector. 3, 6, 2, that's another vector. And 2, 10, -4, that's another vector. These three vectors, if you were to plot them in the R3 space, they would only intersect at the origin. So that's where it's kind of like, there's a relationship, there's a similarity between P2 and R3, but at the same time, they're a bit different when you just look at them individually. If I look at P2 and I look at the graphs of these, it's not necessarily the same thing as the vector is the vectorial representation of each of these polynomials. It's not necessarily the same thing. I just want to make sure that's clear.
Thank you.
Yeah. That's a good point though. Okay, so far we've seen linear independence among polynomials, among matrices, and among our standard R3 world, or yeah, R3 in the particular in this example, R3, right? So now the question is, can we or how do we speak of linear independence for functions? So what do we use to demonstrate linear independence with functions? So this is a bit different, a different approach. So linear independence of functions. So functions are a bit more special than the other objects that we've been dealing with, such as the vectors, matrices, and polynomials. Now we have functions. So for this, we need to use what's called the Wronskian. We use the what's called the Wronskian. The Wronskian to determine linear independence linear independence of functions. And what is the Wronskian? So suppose we have n functions that are all n minus 1 times differentiable. So you can take the derivative of each function n minus 1 times. And it's on the interval negative infinity to infinity. So for functions, for n of them that we have, each of those functions are n minus 1 times differentiable on the interval negative infinity to infinity. Then we call w of x the determinant. So determinants appear once more of f1 of x, f2 of x, fn of x. So the first row are the entries of the first row are the functions that we have, the n functions. So the first row indicates the n functions. Are the n functions. The next row will be the derivative of those functions. So first derivative, so f1 prime of x, f2 prime of x, and fn prime of x. And we do this n minus 1 times. Each row is the third row would be the second derivatives, the fourth row would be the third derivatives, and the last row, the nth row, will be all of the n minus 1 derivatives. So this determinant is considered what's called the Wronskian. Now, determining whether they're linearly independent will boil down to demonstrate whether the Wronskian is 0 or non-zero on the interval um, negative infinity to infinity. So let's look at an example. So suppose I have the, let's see. Yeah, let's make this. Suppose I have the function 1, the function sine of x, and the third function sine 2 of x. So I have 3 functions, and they're linearly, well, we have to determine whether they're linearly independent or not. So we have to use a Wronskian. So use the Wronskian. Now, what's the Wronskian? Well, the first row is 1 sine of x, sine of 2x. And then the next row would be the first derivative. The first derivative of 1 is 0. And then the derivative of sine is cosine of x. And derivative of sine 2x is 2 cosine of 2x. Do it one more time. 0, this would be negative sine of x. And this would be negative 4 sine of 2x. The Wronskian sounds like a dance move. Yeah, well, yeah, do the Wronskian, why don't you? So then now we have to find the determinant. And what makes the most sense is to do the cofactor expansion, right? Along the first column. Because of the zeros. So see, this is when knowing how to compute determinants can be helpful. So then if I use the 1 here and I strike through everything, the first column and the first row, I have a smaller determinant, cosine of x. This is 2 cosine of 2x. This is negative sine of x. This is negative 4 sine of 2x. And then when you perform the determinant, you get negative 4 sine of 2x minus 2 sine, oh, whoops, I think I forgot something. This is minus 4 sine 2x cosine of x. And then this is minus negative 2 cosine of 2x times sine of x. And so this will equal negative 4 sine of 2x cosine of x plus 2 cosine of 2x sine of x. And so what we have to do now is to determine whether or not this equals 0. Is there a point in time when this doesn't equal 0? So that's the idea. Does this equal 0? Or does it never equal 0? If it never equals 0, then they're linearly independent. If there's at least one point, at least one x value that is 0, that makes this equal to 0, then they're linearly dependent. So it looks like we may have to use some trig identities here to see if we can simplify things a bit more. So let's see. So what if I rewrite this as its equivalent form? Negative 4, this is multiplied by 2 sine of x times cosine of x. So I would get negative 8 sine x times cosine squared x. Now how about this guy? Cosine here. Um, let's see. What if I do 2 cosine squared x minus, sorry, should be plus 1. Because one, yeah, it should be 2 cosine x squared x plus 1. So this is 2 multiplied by 2 cosine squared x plus 1 times sine of x. Let me just see if that's... Whenever you don't remember this, always remember that this is equal to cosine squared x minus sine squared x. And so then cosine 2x, if you do 1 minus, or if you do, so this is equal to 1 minus 2 sine squared x, or this can equal, pardon me, this should be cosine squared x minus 1 minus cosine squared x. So yeah, this should be minus 1. It should be 2 cosine squared x minus 1. So that's the one. And this becomes plus 4 cosine squared x minus 2 sine of x. I feel like no one remembers the trigonometries. Yeah, as long as you remember this, you should be good, because then you can replace cosine squared x with its equivalent 1 minus sine squared x, and you get this. Or you can replace sine squared x with its equivalent 1 minus cosine squared x, and you get this. So that's why you have 3 representations for cosine of 2x. So the thing is, this gets a little crazy because of the squares of cosine and sine. So let me just see. There has to be a way to clear things out a bit better. So what can we do? We can write this as cosine squared x is negative 8 sine x plus 4 minus 2 sine x. Does this equal 0 at all? This is a very interesting example. The reason why is because there's 3 different representations of this, and possibly the one that I chose does not give me a clearer way through. We got cosine squared. So cosine squared, I was thinking would be helpful here, but let's see. So if this gets too complicated with the trigonometry here that we have, the best way, the next alternative would be to graph this and to see whether or not it ever crosses 0. But I'm trying to see if there's a better way of dealing with this cosine. You know what might be better? It might be better just to leave this. Actually, let's do this. Let's go back here and let's just leave this as 2 cosine 2x sine of x, because I have a sine and a sine here that I can factor out. I got sine of x. Oops. Sine of x. And this becomes negative 8 cosine squared x plus 2 cosine of 2x. Do you guys see this? So again, the idea is that is there any x value? Yeah, it did, right? Yeah. Is there any x value that makes this expression equal to 0 at all? And if you notice, in factoring in this manner, sine times what? Sine of x times this expression equals 0 when what? When x equals 0. if I plug in 0 into sine of 0 is 0, 0 times whatever is 0. So what did I just show? I showed that the Wronskian does equal 0 for a value of x on the interval -infinity to infinity, which is 0. If that's the case, then we say there. Yeah, so if that's the case, we actually say that this is linearly independent. So it says that it's not identically 0. Let me just see 1 second. Yeah, so it's a bit opposite. So, okay, so the Wronskian, we have to demonstrate actually to show that something is linearly independent. We have to demonstrate that the Wronskian is non-zero for some value of x. So we're expecting it to equal 0. We just want to figure out whether there is a value of x that doesn't make it equal to 0. So that's the real question. Is this non-zero somewhere? Normally it would be 0, but is it non-zero somewhere? And for what value of x? So we know that when x equals 0, this whole thing equals 0. Is there a value that doesn't equal 0? Is there a value of x that wouldn't make it equal to 0? So what I'm going to do is write it this way. Sine of x times -8 cosine squared x plus 2 times cosine squared, 2 cosine squared x minus 1. This would be -8 cosine squared x plus 4 cosine squared x minus 1, minus 2. And this is sine of x. This would be -4 cosine squared x minus 2. I can factor out the -2 and I get -2 sine of x, +2 cosine squared x plus 1. So this is the Wronskian, okay, in its most simplified form. And is there any x value that would not make this 0? Is there an x value? Well, yes. Choose a value. If you notice here, this expression here will always be positive. So this will always be a positive number. Even if you make this equal to 0, this will always be a positive number. So I have a positive number for all x. Just choose any other x value that doesn't make this 0. For example, make x equal to pi over 4. What happens when that happens? We get -2 times sine of pi over 4 multiplied by 2 times cosine of pi over 4 squared plus 1. This would be rad 2 over 2 times -2. This is 2 times a half plus 1. So obviously what happens here, we got negative rad 2, we got 1 plus 1. So we get -2 rad 2. This -2 rad 2 would say what? Non-zero. If this is non-zero, the Wronskian, is not identically 0 on the interval -infinity to infinity. Why not? Because I just found one. I found an x value, pi over 4 in particular, that makes the Wronskian non-zero. So because it's non-zero at least one particular point on the interval -infinity to infinity, then we say what? Then we say that our functions f1 of x equal to 1, f2 of x, which equals sine of x, and f3 of x, which equals sine of 2x, they are linearly independent functions. Okay, so that's how we determine for functions whether they are linearly independent. We use something that's called a Wronskian, which are the rows of the functions according to their derivative. So the first row is just the regular functions, and then the second row will be the first derivative, so on and so forth. You perform the determinant, and you want to figure out, because my determinant is a function of x, as you notice, this is a function of x. My determinant when I compute it is a function of x. This was my determinant here. This is my Wronskian. And what I'm asking is my Wronskian at all ever non-zero? If it's non-zero for one particular value of x, which in this case was power 4, it was non-zero, we say that the set of functions is indeed linearly independent. If we get an expression where it always equals 0 no matter what we plug in for x, then we say that the functions would be linearly dependent. They would be linearly dependent functions. Okay, so that's the idea. Yeah, so when there exists an x value for which the Wronskian in itself is non-zero, at least 1 point, that makes this a non-zero determinant, right? Then we say they're linearly independent. If there is no x value that makes the Wronskian non-zero, which means that it's always 0 for no matter what the x value is, then we would say that the functions are linearly dependent. Yeah, it was the other way around. I had it backwards myself, because normally we care about whether it's only 0, and in this case for Wronskians we care that it actually doesn't equal 0, meaning that the Wronskian doesn't equal 0. So that's the only difference between showing linear independence with functions and linear independence with everything else. So that's the idea. Okay. Yeah. And so that's the idea. That's the idea. And it's not that it's completely different. It's pretty much similar. It's similar to what we've been doing, but it's a little different because it's the nature of the objects that we're dealing with, which are functions themselves. And these functions are not as clean, for example, as vectors or as matrices. These functions can be anything. They could be exponential functions, they could be trigonometric functions, they could be polynomial functions, and so on. Okay. So any questions about the Wronskian? No, no questions. Okay, so now we have several ways to show independence and several ways to show independence for different kinds of objects that we're dealing with now in different types of vector spaces. So then now the question is, what's so significant beyond the fact that we can show whether a set of vectors are linearly independent? What's so special about showing whether a set of vectors span a particular space? Like what's so special about it? Well, the thing is that if you have a set in a vector space, a set of vectors in a vector space that are both linear independent and that span the entire space, those sets of vectors are very special, and they're called bases or basis. So this is the next step in the world of vector spaces, is to deal with what are called bases. A basis is one set, and bases are more than one. So a basis is a set of vectors of a vector space that do both, that where the following holds, where the two following characteristics hold. The first thing is it spans V. And let me just say, the set of vectors, what I'm speaking of is, I'm gonna call this set S, is the set V1 all the way to Vn. Okay? So when I say it spans V, what I'm saying is that the span of S is V. And we know what span is, right? It's the set of all linear combinations. So if I take this set V1 through Vn and I take all linear combinations, all of them possible, I would get everything in V in my vector space. So that's the first step to be a basis. The second step to be a basis set is that the S is a linearly independent set. So now we're making the distinction between sets that are both spanning sets and linearly independent, compared with versus sets that are only spanning yet they're linearly dependent. Or you have sets that are linearly independent but can't span the space. So we have like three different scenarios. We have sets that of vectors that are linearly independent and that span the space, vector space. These are very special ones. These are called bases. But you have other vectors that either are spanning, they span a set, but they're linearly not independent, so they're dependent. Or you have sets that are linearly independent, but they don't span the space. And you can see that very easily with the R3 example. So this is X, Y, Z. Remember, we looked at these basis vectors here, the E1, E2, E3. We've been calling them basis for since the beginning, but I never defined to you what a basis was. And now you have a better understanding what that means. So for example, just as an example, consider the set of vectors E1 and E2. Is this a basis? Is S a basis for R3? So what checks out? What do we know that checks out immediately? Is it the independent condition for basis or the spanning condition?
The span.
It's the span.
Yeah.
So so what you're saying is, give me any vector, no matter what vector it is in R3. So for example, I give you a vector out here in R3, right? I'm gonna call this V. What you're saying is that this vector V can be written as a linear combination of only E1 and E2.
Yeah, no, that's my bad. I thought it was R2 for a second.
Yeah, no, we're talking about R3. So see, now there's a distinction you have to make. What we talked about last time, what do we talk about when we referred to this set particularly? The span of this set S is what? The span. If you take all linear combinations of E1, E2, what do you get? The span is what?
The XY plane?
The XY plane. And we're talking about the plane. But now we're talking about the whole three-dimensional space, R3. So do these two vectors alone span R3? Obviously, it doesn't, because the span, the best that this can do together, those two vectors together, the best they could do is to create the xy plane. Everything that's above the xy plane, there's no way that I can ever write any vector such as the one that I just drew over here. I cannot write a vector that's outside the xy plane as a linear combination of e1, e2, because e1 and e2 can only express vectors as linear combinations of themselves if they're in the xy plane. So this is an example. This is an example of a linearly independent set that does not span the vector space. So this is no. No. Although S is linearly independent, it does not span R3. Do you guys understand what I'm saying here with this? It's just a simple example of a set that's linearly independent yet does not span the vector space. So is it a basis? It's not. What is it missing? It's missing the spanning quality. Now, of course, if I include one more vector, which would in this case be E3, E1, E2, E3, they are all linearly independent, and you can, and I think we've shown that last time. And they're linearly independent, and not only that, they are what? They do span all of R3. So E1, E2, E3 themselves are a basis for the space R3. So I'm gonna give you an example in R2. So let's go back to R2. I have E1, I have E2, and then I have a vector somewhere out here. Call it V. Call it 2, 3. So I'm gonna call this my new space, my new set. I got E1, I got E2, and I got V. Now, is this set, is S a basis for R2? So Mir, you say it is? This is a basis for R2. So then your response would be why? Why would this be a basis?
Well, the span is easy, but it would also be linearly independent because the only solution
So it would be linearly independent.
is 0. I would think so.
Okay. So let's make sure of that. So the span of S, I agree with you. The span of S is indeed R2. It is, right? Because take any linear combination of E1, E2, just for these two alone span R2. So the moment you add in an additional vector, it doesn't affect the span itself. So E1, E2 already takes care of spanning by themselves. You add one more vector, it's not going to affect the span. It's still going to span everything, right? So this span R2, no problem. Now the problem deals with independence, linear independence. Why? Because C1, E1 plus C2, E2 plus C3, V. Does this equal 0? And does it only, so the question is, obviously zeros will work for this equation, right? And the thing is, the zero solution always works for homogeneous systems. It always is a solution. The question is it the only solution? That's the question. So we have C1, right? This is what? 1, 0 plus C2, 0, 1 plus C3, 2, 3. Does this equal 0, 0? And then the question is C1, 0 plus 0, C2 plus 2, C3, 3, C3 equals 0, 0. And then when you put this all together, you get C1 plus 2C3 and you get C2 plus 3C3, this equals 0. And then you get the coefficient matrix 1, 0, 2, and you get 0, 1, 3. That's my coefficient matrix. This is C1, C2, C3, and I get 0, 0. Okay? Now, what happens with a coefficient matrix like this? I don't know if you remember. This is already in row reduced echelon form. What do we have? We have 2 pivots. But then how many variables do we have? We have 3. So remember what happens? This column right here would represent, so this is C1, this is C2, C3. So C3 is what? Is a free variable. Remember about free variables? Remember about this? So this is C1 is equal to negative 2 C3. C2 is equal to negative 3 C3. And C3 is equal to C3. And normally what we do is we treat this as a variable, another parameter, and we get something like this. So look at this, guys. So what's our solution space? Remember, this is a solution space. Remember, the solution space itself is a subspace. So solution space is for everything that's in this solution space C, I have something that looks like this: negative 2, negative 3, t, or in other words, t is a multiple of negative 2, negative 3, 1. What did I just show? A free variable indicates that there are infinitely many solutions. Just plug in anything for t, and you get another vector. You have infinitely many. So this is not linearly independent because I can plug in negative 2, negative 3, 1. I can plug that in here, negative 2, negative 3, 1, and I will get 0. So this is not linearly independent. So infinitely many solutions. So this would indicate that S is not a linearly independent set. So if it's not a linearly independent set, then what do we say? S is not a basis for R2. Any questions? Any questions about this? So what's important is that there's several things that we have to discuss about basis, but one thing I want to make sure is this idea of dimension. Now, normally we think about dimension as, okay, 3 dimensions, 2 dimensions. You have 3 components, you have 2 components, 4-dimensional space. You have 4 components. So we kind of think of dimensions as components for up to this point. But dimension can be defined a little differently. And dimension is the number. So the dimension is the number of elements or vectors in a basis for a vector space. And we denote this, we denote it, note, dimension of vector space V is denoted by dim of V. So the dimension is given by the number of vectors in a basis. So for example, R3, what is the dimension of R3? Three. Why is that? Well, we talked about the basis, the standard basis. So now we're gonna talk about standard stuff. The standard basis of R3 was what? Was E1, E2, and E3. The bases are not the coefficients. The bases are the vectors themselves. There's three vectors, E1, E2, E3, and that makes the basis set, standard basis set for R3. Yes, Mir?
Why is it called the standard basis? Can I have other bases that are not E1, E2, E3?
And the question and the answer to that is of course. So we're always going to start with the most simple kind of thing, right? When we talk about something new, such as a basis, the most simplest kind of basis in the world of R3 is E1, E2, E3 due to the simplicity of such a set. This is the most simple, this is as simple as it gets, guys. You get a whole bunch of zeros and a whole bunch of ones. That's pretty simple to me, right? So we call this standard because it's simple. But of course, so this is what happens. The number of vectors in a basis will never change. So in R3, the number of basis elements or the basis vectors have to only consist of three things. It can't be four, because the moment you have four vectors in R3, the very moment you have more than three vectors, immediately you become a linearly dependent set. Immediately. Because if you had four vectors and you say, hey, this is a basis, then you would say, then what would it mean? In R3, you went from saying you have a dimension of 3 to a dimension of 4 in R3. R3 is only one dimension. You only have one dimension for R3. For each vector space, there's only one dimension to it. So E1, E2, E3 is a standard basis because it's linearly independent and because it spans all of R3. Now, the question is, are there more than just this standard basis? And the answer is of course. And that's where we're headed to. We're headed to a world where we're not only going to be dealing with the standard basis anymore. We're going to be dealing with vectors that, as long as the three vectors that you give me are linearly independent and they span all of the space R3, then they are another vector, basis vector set of vectors for R3. And there's infinitely many bases for R3, for example. You can choose a plethora of three vectors, and as long as they're linearly independent and they span everything, then we're good. So like literally you can select three vectors in space. And this is something that's kind of related to what you said earlier, Mir. As long as these three vectors that you select, they only intersect Like for example, something like this. If they only intersect at the origin like this, then these three vectors are linearly independent geometrically because there's no scalar multiple of one or the other. And they're going to span everything because there's three of them. So we're going to talk about that, but not today so much in terms of the different bases, but we're definitely going to touch upon this next week for a fact. Okay, so dimension 3 has R3. So what about, for example, P2? We talk about P2 a lot. So P2, remember, is the space of polynomials with degree less than or equal to n, or less than or equal to 2. What do you guys think the dimension of P2 is? It's 2 because you see the number 2, right? Remember P2, I said, is similar in its structure to R3. So that's another thing. Vector spaces with similar structures have the same dimension. So P2 is the same as R3 in terms of dimensions. It's 3. Now, what are the standard bases for P2? And we touched upon this in one of those homeworks that we had a while ago. Remember this? This is the standard. Now we can talk about it. Now we can talk about it freely. The standard basis for P2 is similar to E1, E2, E3. Similar. Now remember what I said. So something in P2, right? In P2, what do we have? We have something that looks like this. We have A, and I think this is where we do like the C plus BX plus A squared. Normally we write it AX squared plus BX plus C, but let's just switch around C plus B plus AX squared, right? We can treat this as a vector, CBA. But CBA lives in what? Is in R3. And what are the elements in R3? What are the standard basis elements of R3? 1, 0, 0, right? Then the other one is 0, 1, 0, right? And then the last one is what? 0, 0, 1. But if you convert that back into P2 space, what does 1, 0, 0 correspond with? It corresponds with having a polynomial that looks like this: 1 plus 0x plus 0x squared. And what does 0, 1, 0 correspond with from R3 to P2? It would be something that looks like 0 plus 1x plus 0x squared. And then what does 0, 0, 1 become? 0 plus 0x plus 1x squared. So then the standard basis elements in R3 would lead you to believe that the standard basis elements in P2 would be what? 1, x, and x squared. I hope this makes sense now more than when you first were exposed to this idea of standard basis. So this is standard basis for this, and this is standard basis for this. Again, if this doesn't make sense, please let me know. Please. Does that make sense, guys? The standard basis stuff? This idea of standard basis? And so we have the standard basis for R3. We have the standard basis for P2. So these are vector spaces that we have seen a lot of. And how about the standard basis for M22? First of all, what do you think the dimension of M22 is? That's right. It's 4. So this idea of dimension, remember, we normally consider dimensions to be the number of components. If you look at an element in M22, right? So if we look at M, let's say A. Let's say A is an element in M22. Then A is what? Has a component A, B, C, D. How many components does a matrix in M22 have? It has 4 components. And that's where this idea of dimension also comes into play. So dimensions can be considered as the number of components of an element in the vector space, or it can be considered as the number of basis elements. That's 2 different perspectives of what dimension is. So then don't you see that this is similar to what? What is this similar to? What other vector space M22 has 4 components? The obvious one would be what? R4. Exactly. So we can treat things in M22 similarly as things in R4. So then what would be the standard basis vectors for M22? So first of all, what are the standard? Exactly. It's 1 0 0 0 and 0 1 0 0. That's standard basis for what? Exactly. That's the standard basis for R4. R4 is going to be E1, E2, E3, E4, where it's going to be 1 0 0 0. This would be 0 1 0 0 and ... so on and so forth. So M1 would be what? Would be 1 0 0 0. For example. And this here would be what? 0 1 0 0. And this would be what? 0 1 0 0. And this would be what? 0 0 0 1. And then you can prove it. You can prove it by saying, well, this is a basis for M22. Why? Because they're linearly independent. Linearly independence is pretty straightforward to show, right? So C1, M1 plus C2, M2 plus C3, M3 plus C4, M4, this equals 0. Let me write this over here. So that's to show this is linearly independent. That's the first thing. Or the second thing. So this is M4 equals 0. And I can show very easily that C1, C2, C3, C4, this all equals 0. And then how do you show that something spans? How do I know this spans? This spans M22. How would I do that? Does anybody know how to show that? Ooh. It's kind of like the same way as linearly independence, but now we're going to do C1 M1 plus C2 M2 plus C3 M3 plus C4 M4. When you say something spans, it means what? It means that any element in or any matrix, for example, in M22 can be written as a linear combination of M1, M2, M3, M4. So any of them. So choose an arbitrary one. What's some matrix in M22? Well, it's the matrix that has A, B, C, and D in them. This is an arbitrary vector. So do you notice arbitrary matrix, I should say? Do you notice how linear independence and span are similar yet distinct? They're similar because the setup of the linear combination idea is the same for each. The difference is linear independence, you're setting this linear combination equal to 0 or the 0 element in your vector space. And you want to show that the coefficients are all 0 and only 0. For spanning, you're doing the same idea of linear combination, but now you're choosing an arbitrary, a generalized example of an element in M22. So it doesn't have to be 0. It just could be any other thing. It could be A representing some other number, B representing some other number, C representing some other number, and D representing some other number. And because this is so standard, we get C1 equals A, C2 equals B, C3 equals C, and C4 equals D. What does this mean? This means that give me any vector in M22, every entry here will be a coefficient of the M1, M2, M3, M4 matrices. So this here implies spanning. M1, M2, M3, M4 spans. M22. Why does this span again? Because this is an arbitrary vector, and I just showed you that for any given arbitrary vector, the coefficients are found. They're simply the components of that matrix. And this is what goes for any matrix in M22. So because any matrix can be represented as a linear combination of M1, M2, M3, M4, then it spans M22. That's how you would show it. Okay, great. Great. Any questions about this? Okay. Okay, so let's do something now. So now we understand, right? We understand that the a basis, a set of basis elements or a basis of a vector space is a set that is both a linearly independent and that spans the entire vector space. We've seen the very common examples of vector spaces such as R3, such as M22, and such as P2, right? The polynomial space, the matrix space, and the for three-dimensional space that we normally deal with. And we know about their standard basis for R3, standard basis for P2, and standard basis for the set of 2x2 matrices. Okay. So I'll give you some other problems here. So suppose we have a subspace of R4 consisting of vectors of the form. So I'm gonna call W the set of vectors that look like the following. X1, negative 2x1 plus x2, 9x1 minus 7x2, and negative 3x1 plus 3x2. So suppose that I have this subspace. The question I'm going to ask is find the basis. Find the basis for W, not for R4. I'm not looking for the basis for R4. I'm looking for the basis of the subspace. Find the basis for W and find dimension of W. So how would I find my basis? Well, it's very straightforward, actually. if you look at the vector here that we have, an arbitrary vector in R4 that's in this subspace, I can rewrite this as the following. X1, I can call this 1, -2, 9, -3, plus X2. This is 0, 2, -7, 3. So what did I just do? I just rewrote this and I split this up, utilizing the different variables, x1 and x2. How many elements, how many vectors do I have? I got 2 vectors. Are they linearly independent? That's the first thing I have to try to figure out. The second thing I have to figure out is, does it span the space W? Well, the moment I did this, the moment I rewrote this vector as a sum of 2 vectors, this is immediately what? This is immediately written in a linear combination format. This is a linear combination. And what I'm saying is choose anything for x2, anything for x1, and I create a new vector. So because x1 and x2 are scalars, these are my scalars, and these are my vectors, then W is spanned by these vectors. So for a fact, W is spanned by my vectors. It's the span of 1, -2, 9, -3, and 0, 2, -7, 3. So that's almost a given by the way this is constructed. Now, are they linearly independent? So then what's the question with linear independence? I do C1 of what? 1, -2, 9, -3, plus C2 of what? 0, 2, -7, 3. This has to equal what? 0, 0, 0, 0. Now, are they linearly independent? I can do the whole matrix equation thing here, right? And then do the row reduced echelon form. But I just want to show whether C1, C2 have to be only zeros. Well, the nice thing is, what do I have in the first component? C1 times 1 plus C2 times 0 equals 0. Well, doesn't this mean that C1 must equal 0? Isn't C1 must be 0 because of this first component? Then that's a fact. So this whole thing is 0. So forget about this now and look at C2 only. C2 times 2 equals 0. What does that mean? Doesn't that mean that C2 must be 0 as well? And can only be 0. So then what do we know? These vectors are what? These vectors are linearly independent. So not only do they create a span, not only do the linear combinations of them create the span for W, they're also linearly independent themselves. So then what do we say? What do we say? Call it B. So B, I'm going to define it as the set of 1, -2, 9, -3, and 0, 2, -7, 3 is a basis for W. Any questions about this? Is this clear? Could you go over the span part? Yeah. Well, the reason why the span is almost like given to us because the way the subspace was defined, the subspace of R4 called W is defined as the set of vectors that have this form. They have this form where x1 and x2 are the only variables. So these things change. Choose an x1, from the scalar, the group of scalars, and choose an x2 from the group of scalars. You plug them in here and take all of them, all those possible ones, all those possible combinations of x1 and x2s, no matter, and there's an infinite number. This is a subspace. Now, when I disassociate them, right, when I separate this kind of format of the vector, the way it's represented, when I separate them in terms of x1s and x2s, what do I get? Don't I get two vectors? I get this vector here being multiplied by x1, and I get this vector here multiplied by x2. What am I doing? I'm just rewriting W as a sum of two different vectors. Not just a sum, I'm talking about a linear combination. I literally just said W is this. W is what? A linear combination of these two vectors. This is what I'm saying. So it's given that W is the span of these two vectors. Why? Because W is defined as a vector that looks like this, but this vector that looks like this format can be written as a linear combination of these two vectors. So because of that, we have that W is spanned by these two particular vectors. So they're spanned by these two vectors. And then we just showed that these two vectors themselves in R4 are linearly independent. Immediately, we're able to show that C1 and C2 must only be 0. So they're linearly independent. So because we have a linearly independent set, and we have a set that spans that subspace, then our conclusion is that this is a basis for my vector space W. And since it's a basis because it spans it and it's linearly independent, what's the last thing we say? The dimension of W would be what? What would be my dimension?
2.
It would be 2. Why is it 2? Because I only have 2 vectors in my basis. And another way to define the dimension of a space, whether it be a subspace or a whole vector space, would be how many elements are in the basis. And we found the basis that has 2 elements, 2 vectors. So the dimension of that subspace W is 2. And that's very important from now on to understand that the number of basis vectors for a vector space or for a subspace represents the dimension of that vector space or subspace.